Thanks very much, and yeah, nice to be here. And it's going to be a bit of a talk on how hardware solves problems that creates some of the trustworthiness issues in AI, and kind of how we get to the problem while everybody else is talking about how we solve the problem. So as a hardware startup, we're developing a technology that we call VISC. Versatile Intrinsic Structured Computing. I'll talk more about the architecture as we go through, but our initial focus, and this is very much work in progress, we're a handful of people in a startup creating the technology and implementing it into hardware. And initially it's aimed at solving problems with other microprocessors, not problems that other microprocessors have, but combining with other microprocessor architectures to accelerate and enhance the capability and solve some of the problems that we're being presented with today in hardware. A bit about me and my background, which is about 40 years in the semiconductor industry. At MEMEC, a high-tech distributor of chips, I cut my teeth on what were then considered to be high-performance microprocessors and custom chips, gate arrays. And we solved problems, for example, people kept making too much data and didn't know where to store it, put it on tape drives. How do we connect tape drives? We need a chip for that. So relatively slow data rate, and we solved that particular problem in an ASIC in a 2-micron process. Massive stuff compared to what we're with today. Oxford Semiconductor kind of span out of that problem-solving approach, and we solved problems with, like, again, people made too much data, and we were storing it instead of on tape drives on rotating media, and faster read and write speeds, and we solved that particular problem with a chip made out of 180 nanometer silicon process. Again, just giant by today's standards. And as we move down the list, I've sort of gone on and on, effectively creating businesses that solve existential problems through the magic of silicon. It exists. We can do great things with it, so just keep on using it while other organizations and companies are solving future problems with new materials, new processes, etc. We would take a process that is available to us to solve a problem that exists right now. And that's what we're bringing into Red Semiconductor. And the problem is the equation of cost effectiveness and performance and power consumption of processing to solve real problems. And today we'll talk about the AI aspect of problem solving. So there's a perception. You turn on the radio or TV, and the perception that you get is that AI equals ChatGPT with three arrows and the equals sign. It's bigger and broader than that, but at a generative AI level, which I think encompasses a lot of thinking, it's a huge number of people using a largely centralized resource to create information that they're then able to use for whatever purpose they want to use it. And obviously there's a lot of concern over good versus bad usage of that data. But if we move that out to the edge, then it kind of flips. And you basically got no users per se. You've got a bunch of developers who create the systems and the solutions, but you don't have users of it. It just happens. It's embedded. And you do, instead of the wide array of users, you've got a huge number of benefactors. So all of a sudden your instantiations are millions, tens of millions, potentially hundreds of millions, and your benefactors are multiples of that. You know, the entire planet can benefit, or probably will benefit, from embedded AI at some stage in the future. And those factors place demands on the hardware to solve the problems. Effectively, it's can you make enough of them, and can you make them cheap enough to solve the problems? And that's what we're driving at with with Red Semiconductor. So across a whole bunch of applications, we're seeing trends that create the challenges that we're aiming to solve. So the edge technology in transportation, obviously safety is the issue. And I was at a conference where somebody said, well, it's obvious, isn't it? 99% of road accidents are caused by human beings. Don't let them drive cars, let computers drive cars. There's a big gap between saying that and actually making it happen, with many aspects of problems to be solved and some artificial intelligence that's required in there. And down through the other applications of healthcare, industrial, etc., then we see numerous problems evolving, often driven by the amount of data that we're just trying to create and process, and the speed at which we need to process that data and make sensible decisions on that data. And at the bottom of all this, the privacy and security of that data is really, really important. Whether it's at a personal bank account, bank number details, or at national security level, data that is secure needs to be kept secure. So, again, just sort of looking at some of the driving forces as we consider decentralized and edge-based processing. These applications are necessarily high volume. And the security aspect of that, as soon as you start to transfer human decision making into computers, then you absolutely get a safety factor issue, perceived or real, has yet to be discovered. And the price tag is always going to be an issue. We've seen the images on TV of supposedly cars with almost supercomputers in the boot towing a power station behind them to power it, and that's the future of autonomous driving. Well, it's not, but people like to put it forward as such. So I think a lot of the driving forces come down to solve the problem that exists with what you've got today to solve that problem. Get it done. There's always something down the road that's going to be better, but solve the problem as quickly as possible. And again, back to security and privacy of data as being important. And I think in the nature, every industry, we're now seeing the increased cadence of design. You need to develop something new much more quickly than you used to. So waiting around for solutions is less of an option, and we've got to crank on and use what we've got today. So how quickly can we make some processing architecture, create an architecture that delivers better performance, cost, power combination? So what are we actually doing? So many edge applications are taking data from sensors. I suppose we're looking here at pushing the edge right up to the processing right up to the sensor. And with those sensors, you're building a situational awareness picture, easy to imagine in a world of autonomous vehicles, but where you're creating through numerous types of sensors. You know where you are, what you see around you, and you're looking for anomalies or patterns or changes to the situational data, and then you're taking some action on it, and that action becomes predetermined or figured out in situ. And obviously this is where AI comes in. And then down the road you're probably trying to share and store that data, so you're making it smaller, making it more secure. So again, security comes in as being a really important aspect of this. So as we have been conceptualizing and implementing VISC, what we're actually trying to do largely is to take the developer away from an understanding of how the processor works, the microarchitecture of the processor, so that they're looking back outwards at what's the problem that needs to be fixed. And that so often comes down to how the challenge is expressed in algorithmic form, how you can create equations or descriptions of it, like going back to a mathematical level largely. And the way we start with VISC is to be able to create a freedom of abstracted instructions. So we can create an instruction set that, instead of sort of nitty-gritty of an instruction set, has simple but parametrically rich instructions that enable the developer to say, I just want to do this, get it done. And this can be mathematical building blocks which are used in those algorithms, or it can actually expand even further than that and actually become quite high functional. And then what the instructions do in VISC is invoke hardware that does clever stuff at a hardware level. And a lot of it is about making sure when we look at how do you get more performance out of a processor, in the old days it was, well, clock it faster and make the gate length smaller. We're running out of options to do that. Moore's law is finished or finishing, so we've got to look at different ways. So it's the efficient pipelining of data through simple processors, making sure that the right bit of data is in the right place at exactly the right time for the instruction that turns up at the right time for the problem to be solved. And we do this through fundamentally creating a vector processing environment, because these applications are doing usually the same thing constantly in real time, time after time after time. Modifying the sequencing of instructions, data fetches, where stuff is put to in registers. Traditionally, everything is in order and is placed in register order, etc. This will, as an architecture, will use various techniques to reorder. Some of those techniques are going to be machine learning. It's what are the resources that are available that now we do it differently from how we did it before, when there were different resources available in the processing pipeline. And we're presenting it initially as a front end to any existing architecture, focusing on RISC-V, but it would be configurable with other architectures as well. Initially the first product is going to sit as a front end to architectures, but as we improve the performance, we're going to integrate it more fully in. By doing that, we know more about the resource availability and usage within a processor pipeline, and we can eke greater levels of performance out of that. So at a sort of simplistic front-end block diagram level, it is reading the instructions in, accessing the instructions. It's decompressing to the target instruction set, a bit like a hardware compiler, and then resequencing everything so that it's most efficiently filling the pipeline of the chip. So the chip itself is at a significant level of efficiency, greater than it would have before. And it's a defensible technology, and patents are in process at the moment. So at a little bit deeper level, I think the most important thing here is this sort of along the bottom. So that's slightly more detail above, but the result of it, and the result of only part of it that we have implemented in simulators today, are, I suppose the important one is to figure, when we stick it on the end of on the front of a RISC processor, RISC-V processor, it immediately quarters the number of clock cycles that it takes to perform an algorithm, in this case a matrix multiply, that might be used in neural networks or graphics rendering, etc. So for a very little bit of functionality on the front, you get 4 times the processing throughput. You also get a huge reduction in the number of instructions that are fetched, 300 and something down to 14 instructions. Every time you fetch an instruction, you consume power and you add latency. So just doing this speeds the overall process up, and you've got data in and out, and while you're processing, you're putting data somewhere where you can then access it later, so you're writing and reading back in data. Well, we halve that. So again, latency and power consumption are hugely reduced as a result of that, particularly if you're having to go to off-chip memory for RAM or ROM. So the way this came about largely was a process of concept and then software simulation and then into hardware with FPGAs. And all the way through, it's an iterative process because the reality of implementation informs the concept and keeps going round. And in this whole process, I've said we're a handful of people in Red Semiconductor, but our network, and networks like this one, of contacts, both informal and formal, are absolutely essential to making this happen. You need a driving force. You need a customer that says, I want this to happen because I've got a problem that needs solving. I'll talk about that in a moment. Or somebody who says, I've got 10 or 20 customers and they all need problem solving, so let's work together on how we do this. So we're working with CodaSIP and transferring this over to a RISC-V core architecture that is out there in use today. And then as we move on down the process, we need to make it work on chips. So we're part of the Silicon Catalyst incubator network, and as a result of that, we'll be using the in-kind partnerships for design tools and design flow, and ultimately for test silicon fabrication. So small companies can do great things with the networks that exist today. So our route to market is initially building blocks onto other processors. It will ultimately become IP at a level of an integrated core, fully integrated to drive the performance ever upwards. And we have optionality that goes as far as silicon, either through chiplets or if we're brave enough to try and do an entire implementation of something that we hope customers want, we can go the full extent of an SoC. So an example of a project that we're working on today, just to try and put a bit of reality on it, we're working with a company on the challenge of identification of it's actually cancer therapy through blood cell analysis. Turns out, so for a hardware bloke, I've got my head around AI, and now I'm having to learn about red sticky stuff and things like that. Sort of areas that when I was trained, when I went to university, never even dreamed of. But here you are trying to develop a working knowledge of a broad discipline of engineering capabilities, which I think is a really important aspect of TechWorks and other networks that are bringing technologies together. Anyway, that aside, so another company is working on microfluidics and sensing using various techniques, optical and electrical, for being able to detect different types of cells. And the cells we want to detect, in a syringe full of blood with maybe 10 billion cells in it, we're trying to find 10 or 20 or 30. And whether it's 10 or 20 or 30 will identify whether the therapy is working or whether it needs to be changed. So it will allow doctors and therapists a real-time analysis of whether something's working, whether they need to change it. So the importance of not missing that needle in a haystack, or a few needles in a haystack, is so important, so important, because you get this number wrong, it can lead to wrong diagnosis or therapies. And so you can imagine there's a huge amount of data pertaining to all sorts of types of blood cells, and somewhere in that noisy, messy data, you're looking for some very sort of distinct patterns, which you've provided the training model. So there is the human expertise is required to define what the training model is and how that's used. But I think that will, in future, become more self-learning, so it can be refined as anomalies are spotted. Human being intervenes and says, that anomaly means this or means that, and next time round you're able to cope with the anomalies. So the output of all this work is going to be a product. It's going to be an instrument that sits on a doctor's desk. So at this small level, the kind of companies that are involved in it, both hardware and software and expertise, the trustworthiness is quite a small world. But you can imagine that the next stages of this move out to, well, if you can use it to identify what you want to, I can use it to identify something else with the same or different body fluid. So can I use it and can I apply my own model to it? And then you might move into areas where you're using it to automate some kind of drug delivery. You're saying, this has changed, so let's up the level of this. So the issues then of trustworthiness all suddenly start to crowd in as you grow the world that this bit of technology operates in. And so it's been really interesting sort of hearing how you validate everything from training models to data sets and use that and make sure that you've got a paper trail of trustworthiness through that process. Anyway, that's the example of our direction of travel with our technology, from small acorns, etc. This is where we're heading. So at the moment, our benchmarks are showing really promising results, and AI algorithms are looking good. We're doing more work on larger and more complex AI algorithms to prove that out. Take something that works. We've taken RISC-V core and add to it, make it better. It doesn't have to be RISC-V. If somebody came along with another microprocessor architecture and said, here's some money, make VISC work with that, then we certainly can. That's not a problem. But our acceleration and enhancement IP is very strongly protectable as we go forwards. So as we move forwards, we're at a software level at the moment, and then moving into the hardware implementation, and we will move all the way to silicon-based products that will go into complex end products. And so the applications are underway, and our goal is to enable our customers to exploit AI to the best and create all those opportunities and issues, I suppose, for how we solve the trustworthiness in AI challenge. But it's got to have the AI working first to make that work, certainly at the edge. So that's where we're focusing.